Hi guys, I would like to go back a little bit to this to talk about this rotational inertia because I would like to talk a little bit more about how to compute the rotational inertia of a solid body by using the integral. Okay, this is because in some AP tests, in some exercises, they may ask you to compute that. In the book, you only have one example, which is this one, the 10.07, which is you have to imagine a thin and uniform rod of mass m and length l, and it has an x-axis in the origin of the rod center, in the center of mass. So they ask you what is the rotational inertia of the rod about the perpendicular rotation axis through the center. It's this example, okay? So to compute the rotational inertia, you have to use this formula. Now, what is the problem always in this kind of exercises is that you have to compute the integral respect to the mass, and usually you don't have that. You have to make a change of variable from the instead of respect to the mass, you want it to respect to the size, okay? To the what are the dimensions? In this case, we want it to respect x. So what do we do in here is usually you have to have this some relation between the mass and in this case the length, and that is the density, but not the density, the volumetric density is the linear density in this case. So, well, because the rod is uniform, so we can say that the mass, the the density of the mass and the x is m over l. Okay, so this is the rod. You can have one differential in here, and this the linear density is n over l. So how do you do it? You just substitute here this dm, the differential with respect to m. You want to put the differential to respect to x, and you end up with this. Okay. So you make the integral. This is cubic, and you get the final answer. Okay. This, for example, in the AP test, they have this example. Okay. Now in this case, you have a triangular rod, and this in this case is not uniform. In this case, the linear mass density is lambda, is this. As you can see, it depends also on the distance on x. Okay. So how do you compute this? How do you do this? So in this case, we have that the as I say, the linear density is this, and it goes from 0 to L. Okay, maybe. So in this case, the rotational inertia, we compute it as usual. This is the usual formula. It's in 1D, so it's just linear. So we only consider the x. And on the other side, we have this linear density, which is computed like this, which we substitute the lambda in here, and we get this. So we just change the differential of m in here, and we plug it inside the integral, so we can compute that you get this, and when you make the integral, you get the x to the fourth divided by 4, and between the x equal to 0 and x equal to L, and this is the final result, which is the same they asking here. Now the rest is I think you can do it. Then you have a hoop in here, and you put 3 rods. So what is the rotational inertia? Well, that's the sum of all of them the total rotational inertia is equal to, well, you have three of these triangular rods plus the rotational inertia of the hood, which is ml squared. So, well, you can compute it, 3 times this plus this. And also they ask to derive an expression for the final angular speed, well, and using this all these variables. And well, you just have, this is the torque, and the different time is equal to the rotational inertia and the angular angular frequency. Yeah. So this is what you get at the end. Okay. So this is how you do this kind of problems. So I think you can practice with this kind of problems by doing this problem 35, in page 289 of the textbook, and problem 37. You can try to solve this kind of problems. I think it's going to be good for you. I will upload these problems as homework in the Google Classroom, and well, I hope this will help us to solve this kind of problems. Okay.